One thing. But when this one just
Thank you very much. Today I was speaking about various interesting aspects of two-dimensional gauge theories with 0,2 supersymmetry. And this work was done in collaboration with Sergei Gukov and Pavel Kutro. I should also mention that what I spoke about yesterday regarding the connection between four manifolds and 0,2 theories was also done with collaboration of Sergei Gukov and Pavel Kutro. So in some sense, I already motivated the study of 0,2 theories yesterday because they are so intimately related to four manifolds, and if you care about four manifolds, you should care about 0,2 theories. I guess that's perhaps a better way to motivate mathematicians than physicists. But for a physicist, perhaps another motivation is the fact that 0,2 theories are relevant from the point of view of heterotic model building. And in fact, a lot of work that has gone in to studying 0,2 theories, they've mainly been studying Landau-Gizmo models with 0,2 supersymmetry, was motivated from model building perspective. And apart from that, just as theoretical laboratories of studying interesting aspects of four-dimensional physics, these theories work very well. In particular, they exhibit many similar features as four-dimensional supersymmetric gauge theories, but at the same time, they are way more under control than four-dimensional theories. In fact, I would go so far as to say that in some cases, and for some observables, theories with 0,2 supersymmetry are even more tractable than their higher supersymmetric cousins, namely 2,2 supersymmetric theories in two dimensions. So this might sound somewhat counterintuitive, but the feature that makes it so is chirality. So a lot of mileage about these theories can be obtained due to their chiral nature. What do I mean by that? So by 0,2 theories, I mean that the theory has two supersymmetries and both are charged the same way under rotational symmetry in two dimensions. So that naturally allows for field content with different number of left moving and right moving fermions. And that's one of the crucial things about 0,2 theories. So different number of left and right moving fermions. Why is that? So if you remember, anomalies in two dimensions are computed by bubble graphs like this, where in these loops propagate fermions. Insert, if it's a chiral anomaly, you want to insert a matrix gamma 3, which is measuring whether the fermion is left moving or right moving. And if you have different number of them, in general, for a generic 0,2 theory, global symmetries are going to have non-vanishing 't Hooft anomalies. Just because different number of left and right moving fermions are contributing to this diagram. So, as a consequence of chirality, you get non-vanishing 't Hooft anomalies. under RG flow, who taught us that these anomalies should remain the same. So in the low energy, you should have the same anomaly. Of the global symmetry question. Now, what that means is that if you flow deep into infrared, there is no way your theory is going to be gapped, because you want some degrees of freedom, some gapless degrees of freedom, which are used to saturate this anomaly. So, just this basic stream of logic tells you that there are going to be gapless modes. And then you can ask a very well posed question about low energy physics, namely, what is the autonomous physics that describes the theory of gapless modes? In other words, what is the conform field theory? So, if you see a generic 0,2 theory, this is a very good question to ask about the low energy physics. In particular, because you are always bound to get an interesting answer. And as we will see in the talk, for many seemingly complicated 0,2 theories, this question can be answered very explicitly. Meaning you can always find, in those cases that I'm going to talk about, you can find the exact solution for physics at low energies. So, another comment that I should make about this CFT is that it has a nice property of state operator correspondence. So, we know that there is state operator correspondence for a CFT if the vacuum state is more than So you could see that from the microscopic theory. Let's say you have a gauge theory you want to work with. You can look at its modulus space, and if that modulus space is compact, so that there is no space for the vacuum wave function to spread and become non-normalized, you have this nice property in the low energy theory of state operator correspondence, and that buys you a lot of power, in particular because these global symmetries that we talked about, they get promoted to chiral symmetries. Global symmetries get promoted to chiral symmetries. What do I mean by that? When you have a current, a conserved current, it satisfies this equation in general, or if you wish, but when you have state operator correspondence, you can actually argue that this equation gives you two equations. How so? So, because you have state operator correspondence, you can create a state in the CFT by acting on the vacuum by, let's say, Jz. And Jz, because it has only Z index and not Z bar index, it scales only with respect to the holomorphic Virasoro algebra. In particular, it is annihilated completely by anti-holomorphic Virasoro algebra. In particular, it is scaled by L minus 1 bar on Jz equals 0. And if you translate that back into coordinates, you get dz bar on Jz equals 0. And the only thing that is necessary for you to argue this is the fact that you can create a state out of this operator. once you have these equations, they are very powerful, because what that means is that the current only has expansion in terms of z. So you could use contour integration and integrate jz on some spatial slice with various insertions of powers of z and create infinitely many charges. So this results in infinitely many charges. And as you can guess, it's a very good thing to have. So, for example, the symmetry that appears in WCW models, or the algebra of or the Katsumuri algebra, they all follow from holomorphicity of the current. Okay. So this will also play an important role in the study of 0,2 theory. In fact, as the flow of argument suggests, this is a very generic feature of 0,2 theories. If you want to ask questions like this for a given 0,2 theory, you should always worry whether the theory has a normalizable vacuum or not. And if it does, you have a lot of symmetry at your disposal. Okay. Any questions so far? I mean, this is what makes it possible for us to answer explicitly what this infrared theory is. So, the aim of the talk is to demonstrate how that goes. And to begin, let me first discuss how one can build a 0,2 gauge theory. So, I should say, is the gauge theories that we concern ourselves with, because those are the non-trivial theories that haven't been studied in the literature to a great extent. So we are familiar with supersymmetric construction of supersymmetric gauge theories from 4-dimensional n+1 theory, where you have a bunch of matter multiplets, a bunch of vector multiplets, and you put them together in a consistent fashion, and you got yourself an n=1 gauge theory. In the same way, first up, in order to construct gauge theory, we should first understand what sort of representations are allowed by the supersymmetry. So we should first talk about n = 0,2 representation theory. Or various multiplets that are allowed by 0,2. So in representations, this symmetry turns out to be richer than n = 1 in 4D, in that it offers two types of matter multiplets. Unlike 4 dimensions, where you only have a chiral field, a chiral multiplet, and a matter multiplet, you have two types of matter multiplet. The first is called chiral multiplet. It obeys d bar plus phi equals 0, where phi is a bosonic primary, it's spin 0. And you have another matter multiplet, which is called Fermi multiplet. And this also obeys the chirality condition d plus psi equals 0, where this is a spinor. So one could write down explicitly the component expansion and read off the component fields that would enter in the Lagrangian. So instead of being that explicit, let me just list what they are. So in this case, it involves complex scalar, and a complex right-moving fermion, and in the case of Fermi multiplet, the on-chip puzzle you because we are taught that in a supersymmetric multiplet, the number of bosonic state and fermionic state should be equal. And that is not the case in this multiplet. You only have 2 fermionic degrees of freedom and 0 bosonic degrees of freedom. You would ask what is going on. The resolution is very simple. Supersymmetry only lives on the right. So you can only expect the matching of degrees of freedom on the right moving side. But as I said, these fermions are left moving, so you do not expect, they don't enjoy any supersymmetry, so you don't expect that they would have any partners.
So supersymmetry is singular.
Yeah. And in addition to the matter fields, you have a vector multiplet. Which has gauge boson, vector field, gauge field, the gauging of. But as you know, the degrees of freedom associated with the gauge field in 2 dimensions, the gauge invariant degrees of freedom are 0. So the only on-shell degree of freedom is the gauge node. And if you compute its field strength, the field strength also lives in a supermultiplet, and that supermultiplet is in fact Fermi type. So the field strength multiplet is a Fermi multiplet. Let me denote it by lambda, where the primary or the lowest component is the Fermi, is the gauge node. Now, what sort of interactions one can write down? Of course, one can write down the minimal coupling, the way things couple to the vector multiplet, that is canonically dictated by supersymmetry. I won't go into the superfield formulation of it all, but at the level of components, they simply get minimally coupled to the gauge field. What else? What is the notion of superpotential, for example? The kind of interaction that we write in 4-dimensional n+1 theories. Well, there are 2 notions of superpotential. One is slightly unfamiliar, perhaps. The way you make a Fermi field and a chiral field interact. Well, let me first talk about the familiar notion. Is via a usual type holomorphic term, integral d theta, is integration over half superspace. You have psi and j of phi, where j is some holomorphic function of phi. So you can see this is very much like a superpotential, except that because it's just one Grassmann integral, you insist that they should have one fermion. So this is something called J term. Another way to make psi and phi interact is to write down a coupling of this sort, where you change this chiral condition obeyed by psi to this. So the interaction somehow is encoded in the definition of the Fermi field, and this is called E-term coupling. I should mention that complex conjugate of the Fermi multiplet is also a Fermi multiplet, and if this Fermi multiplet has an E-type interaction, then the complex conjugate has a J-type interaction. So I should say under charge conjugation, C Fermi multiplet goes to psi goes to another Fermi multiplet. It goes to psi bar, which is also a Fermi multiplet, and p-term interaction of this psi goes to j-term interaction of this psi bar, and vice versa. And if a fermion has both E and J type interaction, then in order to preserve supersymmetry, you need to ensure that E dot J equals 0. But in what I will be talking about, I will simply consider this type of superpotential and not E type superpotential. Now, what would a mass term be? So we know in n equals 4 n equals 1 supersymmetric theory, Bode mentioned you can simply write superpotential of the form m phi square, and that gives a mass to the component fields. So what is a similar term here? So the term that turns out to give mass is the following. A J term psi, where J is just a linear function phi. If you expand this in components, you will see that this induces mass term for phi as well as the mass term for psi. But what do I mean by mass term for psi? Psi, as I said earlier, is a purely left moving fermion. It's not possible to give a mass term of that. But phi, in its partner, has a right moving fermion. So what I mean by mass term is a term of this type, where lambda is probably not right. Eta, where eta is right moving fermion inside phi. Okay. So this is my quick review of 0, 2 representation here. Now what we want to do is take all these multiplets, put them together to construct a gauge theory. Please.
What is E dot J?
I'm allowing for multiple fermions. So in general, you could have psi EA, and here
So I mean, does that
and
dot
that
include
case,
the
the dot
theta
means
integral? Does that dot include a theta integral?
no. Just
Or is it both
product.
sides? Okay.
So in particular, if you just have one fermion, you are not allowed to turn both the terms. Any more questions?
Yeah, for sure something stupid. I mean, phi square means that in the Fermi multiplet there is a scalar which is also the same scalar of the chiral one. Because m phi square, the second, I mean, one phi arises from the
Chiral
Fermi phi,
Yeah.
and the other phi arises from the Fermi multiplet.
Sorry, what is other phi?
Is phi square, right?
Yeah, phi square is the same phi. The square of the primary of the phi.
Okay, okay.
So this is the transformation of psi gives rise to some of.
Yeah.
Okay.
Yeah, in some sense related to this, but you can do it with the J term also. I mean, in this term, I guess it would be clearer. Okay. Let me mention another important coupling, which will be useful or which will appear later, is the pi Dilabolus coupling, abbreviated as pi coupling. And the way you write it, so whenever you have an Abhijit gauge group, you can write a term of this type, where this is the Gaugino Fermi multiplet, this parameter. And this reduces to the familiar Fi coupling. For example, if you take T to be psi plus I theta, so 2 pi or something, then in terms of components, this will look like psi integration of d plus theta over 2 pi integration of f, where this is the Lewis number. And this is the d term. The auxiliary field d in the vector multiplet. I didn't talk about it explicitly here, but this d term works the same way as in 4 dimensions.
Excuse me? In the 2,2 case, the phi Filioculus term is just one particular example of the twisted superpotential.
Yeah.
Here there is a notion of twisted superpotential.
There is no notion of twisted superpotential. The only couplings allowed by supersymmetry are J term and E term.
Okay.
So if you wish, you can think one of them as a twisted
Yeah.
but it doesn't really make sense. It doesn't
Okay.
really buy anything. All right. Any more questions?
So there's an R symmetry here,
Yes.
and so I can only write down this mass term where if I coupling, if they have combination has the correct R
Compared
charge.
to large charges, yeah. Or you could take another point of view. You could say that it's the couplings in the superpotential that will determine the R charge at the infrared. So for example, I mean the same thing, you know, if you have in 2,2 theory a phi cube or phi to the 4 superpotential, it's the superpotential that fixes the R charge of phi to be 1/4 or something like that. Yeah, we'll talk about the R symmetry in detail also. It will be important. Okay, let's put them together and construct very simple H3. Namely, 0, 2, n equal to 0, 2 SQED of the following type. So you have a U1 gauge group, coupled to one chiral multiplet, phi, and NF Fermi multiplets. This is with charge 1.